Okay, hi everyone, welcome back to the Comptia Security Plus course, Asymmetric Key Algorithms. Asymmetric key algorithms use a pair of different keys to encrypt and decrypt data. The keys might be related, but they are not identical or even close to it in the way symmetric keys are. The two asymmetric keys are related mathematically. Imagine that you are the night shift security guard for a warehouse that stores CPUs. When your shift is over, you are required to lock up, but the warehouse uses a special lock. Your key can only lock the warehouse door, it cannot unlock it. Conversely, the morning watchman has a key that can only unlock the door but not lock it. There are physical and electronic locks of this matter. This is analogous to asymmetric keys used in encryption. One key is used to encrypt data, the other dissimilar key is used to decrypt data. Because of the different keys, asymmetric key management schemes such as PKI are considered to be the most complicated. Examples of asymmetric key algorithms include RSA, the Diffie-Hellman system, the elliptic curve cryptography. SSL and TLS protocols use symmetric key algorithms, but generally do so in a public key cryptographic environment. Public key cryptography. Public key cryptography uses asymmetric keys alone or in addition to symmetric keys. It doesn't need the secure exchange of secret keys mentioned in the symmetric key section. Instead, the asymmetric key algorithm creates a secret private key and a published public key. The public key is well known and anyone can use it to encrypt messages. However, only the owners of the paired or corresponding private key can decrypt the message. The security of the system is based on the secrecy of the private key. If the private key is compromised, the entire system will lose its effectiveness. This is illustrated in figure 14.1. Public key cryptography can become more intense. In some schemes, the private key is used to sign a message and anyone can check the signature with the public key. The signing is done with a digital signature. A digital signature authenticates a document through math, letting the recipient know that the document was created and sent by the actual sender and not someone else, so it ensures integrity and non-repudiation, and it protects against forgery and tampering. The basic order of functions for the usage of asymmetric keys in this case would be encrypt, sign, decrypt, and verify. In the Diffie-Hellman scheme, each user generates a public-private key pair and distributes a public key to everyone else. After two or more users obtain a copy of the other's public keys, they can be used to create a shared secret used as the key for a symmetric cipher. Due to the varying methods of public key cryptography, the whole subject can become somewhat confusing. Remember that there will always be a private key and a public key involved, and that public key cryptography can use asymmetric keys alone or in addition to symmetric keys. Internet standards such as SSL, TLS and PGP use public key cryptography. Don't confuse the term key cryptography with public key infrastructure, PKI. Although they are related, they are not the same. PKI is the entire system of hardware, software, policies, and so on that binds public keys with user identities by the way of certificates and a certificate authority server or both server or other such device. A certificate is an electronic document that uses a digital signature to bind the key with the identity. Key management. Key management deals with the relationship between users and keys. It's important to manage the generation, exchange, storage and usage of those keys. It is crucial technically and organizationally because issues can present themselves due to poorly designed key systems and poor management. Keys must be chosen and stored securely. The generation of strong keys is probably the most important concept. Some algorithms have weak keys that make cryptanalysis easy. For example, DES uses a considerably weaker key than AES. The stronger the key management. We detail several for the exchange of keys later in this chapter, including encapsulating one key within another using key indicators and exchanging symmetric session keys with an asymmetric key algorithm, in effect ciphering or cipher. Secure storage of keys often depends on users and passwords or other authentication schemes. Proper storage of keys allows for availability, part of the CIA triad. Finally, keys should be replaced frequently. If a particular user uses a key for too long, it increases the chances of the key being cracked. Keys, like passwords, should be changed and or recycled often. Steganography. Although I have placed steganography within the cryptography section, it actually isn't cryptography, although it might be used with cryptography. Steganography is the science and art of writing hidden messages. It is a form of security through obscurity. The goal is that no one aside from the sender and receiver should even suspect that the hidden message exists. The advantage of steganography is that the clearly visible messages look to be just that, regular old messages that wouldn't usually attract attention to themselves. Most people know when they come into contact with an encrypted message, but far fewer people identify when a steganography message has crossed their path. The classic example of steganography is from ancient Greece. A messenger would shave his head and a leader would write a message on the person's scalp with indelible ink. After the messenger's hair grew long enough to hide the message, he would deliver a message. Time was of no essence. When the messenger arrived at the destination, he would shave his head and the recipient could read the message. In Greek, Steganographos means covered, and this is one example of hiding a message by covering it. Steganography can hide messages within encrypted documents by inserting extra encrypted information. The hidden messages can also be found in sound files, image files, slowed down video files, and regular Word documents or Excel spreadsheets. Messages can also be concealed within VoIP conversations known as lost audio packets, steganography or LAC, and within any streaming service as well. They can also be obscured on a compromised wireless network with the HICC-UPS system, hidden communication system for corrupted networks. A common example of steganography is when using graphic files to send hidden messages. In this scenario, the least significant bit of each byte is replaced. For example, we could shade the color of a pixel or triad just slightly. This slight change would change the binary number associated with the color, enabling us to insert information. The color blue is represented as 3 bytes of data numbered 0, 0 and 255. We could change the color blue slightly to 1, 0, 255. This would not make the graphic look any different to the naked eye, but the change would be there nonetheless. This would be done in several or more pixels of the graphic of form to form the message. For this to work, the recipient would first need to have possession of the original file. Then the sender would transmit the modified steganographic steganographic file to be compared with the original by the recipient. There are several programs available on the internet that facilitate and automate this process. Remember that one of the goals of steganography is to provide obfuscation, meaning making something obscure and unclear. This can be difficult to do manually and more difficult to do unmanually, so we use reliable vendor provided tools to aid in the process. Encryption and algorithms. We mentioned previously that ciphers or algorithms can encrypt or decrypt data with the help of a key. We also pointed out that algorithms are well-defined instructions that describe computations from their initial state to their final state. In addition, we mentioned that there are symmetric and asymmetric algorithms. Now let's talk about some of the algorithmic standards within both of these classifications. We start with symmetric keys, including DES, 3DES, AES and RC, and afterward move on to asymmetric types including RSA, Diffie-Hellman and the elliptic curve. DES and 3DES. The data encryption standard DES is an older type of block cipher selected by the US federal government back in the 1970s as its encryption standard, but due to its weak key, it is now considered deprecated and has been replaced by other standards. Being a block cipher, it groups 64 bits together into encryption units. Today, a 64-bit cipher is not considered powerful enough. Also, and more important, the key size is 56-bit, which can be cracked fairly easily with a brute force attack or linear cryptanalysis attack. In addition to this, there are some theoretical weaknesses to the cipher itself. DES was replaced by triple DES, 3DES in 1999. The actual algorithm is sometimes referred to as the data encryption algorithm, DEA. The algorithm is based on the Fistel cipher, which has very similar, if not identical, encryption and decryption process, reducing the amount of code required. Triple DES, also known as 3DES or Triple Data Encryption Algorithm, TDEA, is similar to DES but applies the cipher algorithm 3 times to each cipher block. The cipher block size is still 64-bit, but the key size can now be as much as 168-bit, 3 times the size of DES. This was a smart approach to defeating brute force attacks without having to completely redesign the DES protocol. However, both DES and 3DES have been overshadowed by AES, which became the preferred standard in late 2001. AES. In the late 1990s, the National Institute of Standards and Technology, NIST, started a competition to develop a more advanced type of encryption. There were 15 submissions, including Serpent, Twofish, RC6 and others, but the selected winner was RingDL. This submission was then furthered into the Advanced Encryption Standard, AES, and became the US federal government standard in 2002. AES is the successor to DES and 3DES and is another asymmetric key encryption standard composed of 3 different versions of block ciphers: AES 128, AES 192 and AES 256. Each of these has the same 128-bit cipher block size, but the key sizes for each are 128-bit, 192-bit and 256-bit respectively. AES is based on the substitution and permutation network, which takes plain text and the key and applies X number of rounds to create the ciphertext. These rounds consist of substitution boxes and permutation boxes, usually in groups of 4 by 4 bytes that convert the plain text input bits to ciphertext output bits. AES specifies 10, 12 or 14 rounds for each of the respective versions. AES is fast, uses minimal resources and can be used on a variety of platforms. For example, it is the encryption algorithm of choice if you have a wireless network running the WPA2 protocol. The IEEE 802.11i standard specifies the usage of AES with WPA2 and in the process deprecates WEP. You will also find AES as the encrypting protocol for remote control applications. These are examples of data in motion, also called data in transit. Any network session that uses AES would fall into this category, but memory encryption would fall into this category as well. For example, there are programs that can encrypt passwords and other personally identifiable information PII as it is passing through RAM. They often use AES and 2FISH. In addition, AES is a good choice for transferring encrypted data quickly to a USB flash drive. It is also used as the Windows encryption file system EFS, an algorithm, and in whole disk encryption techniques such as BitLocker. AES is purportedly susceptible to the related key attack if the attacker has some information about the mathematical relationship between several different keys. Side channel attacks can also circumvent the AES cipher using malware to obtain privilege escalation. These are ways of attacking the implementation of the protocol, but not the protocol itself. Generally, AES is considered the strongest type of symmetric encryption for many scenarios. As of now, AES is used worldwide and has not been outright compromised, and some industry experts think it never will be. You may have heard the terms DEK, KEK and MEK. These are different types of keys used during that encryption process. AES provides a good place to discuss these. Let's say you have data that you need encrypted and you decide to use AES to do so. When AES encrypts the data, it does so with data encryption key DEK. To make the encryption system more secure, you can store that DEK in an encrypted format. This is done with the key encryption key KEK and can be stored in a separate location for additional security if need be. A master encryption key MEK or simply master key is another type of key that describes either a DEK or KEK being used. For example, in a secure storage scenario, the master key will be a DEK that is used to encrypt data that is put in a user's protected storage area. It is encrypted by KEK and is based on the user's password. That is a very basic explanation of DEK, KEK and MEK. For the Security Plus exam, you should be able to define them and understand that they can be instrumental in dealing with secure storage of data, potentially in multiple locations. However, unless you are a developer, you most likely won't be working with each type of key individually. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.